Hello everyone, welcome to Sekhwa Education. I am Sukhvinder here again with our next lecture. This is our fourth lecture in the series of steam turbine. Okay, in this lecture we study about the compounding of impulse turbine. Okay, so in the previous three lectures, in the first lecture we study about what is the introduction relating to a steam turbine or a steam power plant layout. In the second lecture we study about the classifications of steam turbine and how we can convert the pressure energy into kinetic energy. In the third lecture we cover about the D-levels turbine, that is the single stage impulse turbine. Now we are studying about a compounding of impulse turbine. Okay, now first of all, what is compounding? Compounding is just a process in which we absorb the either it is a kinetic energy or a pressure energy in number of stages, either in terms of rotor or in terms of fixed blade. Okay, in this case the rotor which is attached to the fixed shaft, we rather than installing one rotor we attach a number of rotors, number of moving blades. Similarly we can attach a number of nozzles sets and number of fixed sets. This process in which we absorb a kinetic energy, a pressure energy in various stages rather than in single stage is known as a compounding of a impulse turbine. Okay, now question comes, what is the need of doing compounding? Okay, for this I mentioned 3 points over here. First point, when the pressure drop is very large, that means the steam which enters the turbine, if the pressure of that steam is very much high, and when we enter that high pressure steam into a nozzle, then that means there is a high drop down of pressure. But practically it is not possible to get a high drop down of pressure in a single stage. That's why a multi-stage system is required, means a compounding is required. Second is, when we change the pressure energy into a kinetic energy, it produces a tremendous amount of kinetic energy. However, practically it is not possible to attain high amount of kinetic energy in a single stage to impart a high energy to a single moving rotor. Okay, that's why we need to divide the velocity into number of stages and also divide the pressure into number of stages. Then third, if for example if we use this high pressure energy and high pressure energy in a single stage which converts into a kinetic energy in a single stage, okay, then there is a large amount of chances to loss of kinetic energy at the exit. As I mentioned in the previous lecture, the outlet velocity for any curve, for either for impulse or reaction turbine, the outlet velocity is similar to the loss of kinetic energy. If the outlet velocity is more, then that means the kinetic energy loss is more, that means the efficiency of the turbine is less. So therefore, to avoid the kinetic energy loss, it is also a better way to use a compounding. So these are the 3 reasons why we need a compounding. Okay, now what are the various types of compounding that we can do in the case of impulse turbine? The first is the velocity compounding. In this we can divide the kinetic energy into a number of stages. Then there is a pressure compounding. In this case we divide a pressure in a number of stages. Rather than converting a pressure to kinetic energy in a single stage, we convert into a number of stages. Then there is a pressure and velocity compounding. This is a combination of velocity and pressure compounding system. In this system we also divide the kinetic energy into number of stages and also divide the pressure energy into number of stages. Okay, now we discuss these 3 types in detail. Okay, now first of all, velocity compounding. I just mentioned one word over here, that is a Curtis impulse turbine. This turbine is the modification of the D-level turbine in which we do a velocity compounding. Okay, in this type of compounding or in the Curtis impulse turbine, there are 3 type of equipments that are attached. First is the set of nozzle, okay, which is attached in the starting, this part. This is a set of nozzle, this is attached to the casing part. Then there is a set of moving blade, these blades, this, then this, and then this. Set of moving blade. This set of moving blade is fixed with the shaft, the main shaft of the turbine. Okay, that means when the shaft rotates or when the moving blade rotates, they both are coupled with each other, means if one moves then the other also moves. Okay, then third is the fixed blade, these blades, these which are attached with the casing. Okay, in this case there is a one set of nozzle in the starting, then there is a alternative set of, first set is moving blade set, then there is a fixed blade set, then again moving, then fixed, then again moving. We can install this up to number of stages. Okay, first stage, let's suppose this is a single stage, this is a single stage, then two stage, then three stage. This combination till here it is a single stage, then this is a second stage. Okay, we can use in a number of stages term. So in this case we having three stages, means we having three rotors, then we having a three stages. Okay, there is another diagram for this. First, this is representing nozzle, these are the moving blades, then these are the fixed blades, these are again the moving blades, then fixed, then moving. Now comes to the working. In the starting, when the steam enters the nozzle converts the pressure energy into a kinetic energy, then this high kinetic energy enters the first moving blade, as it is showing over here. At the starting the pressure energy is high, then kinetic energy is low, then it enters the nozzle. As a result, the velocity increases and the pressure decreases. In this case, the pressure decreases only in the nozzle part, afterwards the pressure remains constant. Then this high velocity steam enters the moving blade, where it loses limited amount of kinetic energy, limited amount of velocity. Okay, then again it enters the fixed blade. In the fixed blade, the basic function of fixed blade is to just to guide the steam which come out from the first moving blade and it enters the second moving blade at a proper angle. Okay, so it just acting like a guide vanes or guide blades. Okay, however, practically there is also little bit velocity drop down in the fixed blades. Then again it enters the moving blade, where it can, again kinetic energy is decreased, which imparts the rotary motion to the rotor or the moving blades. Then this keep on going till the number of stages which we install over here. In this case, the loss of velocity or loss of kinetic energy is very less if we use a number of stages. Okay, so this is the working of velocity compounding, and this is the systematic diagram. This is the pressure and velocity variations. This is a systematic diagram for velocity compounding or a Rateaus impulse turbine. Okay, now we come to the velocity triangles for this. Okay, now this is the velocity triangle for two-stage velocity compounding turbine or a Rateaus impulse turbine of two-stage. I just mentioned over here, this is for the maximum utilization condition. Okay, maximum utilization condition. So there are two assumptions over here. These are two assumptions. These are the notations. Here B is the beta, beta 2 equals to beta 3. Then alpha 3 is equals to alpha 2 dash, beta 2 dash equals to beta 3 dash. Then again this W is the relative velocity. Relative velocity W2 is equals to relative velocity of third. Then again C is the absolute velocity. Okay, which is mentioned over here. Okay, so these are the two conditions. Okay, now this part, how this works. Okay, this diagram, before doing this diagram, there is a lengthy derivation which we needs to do to calculate this part. Okay, so I will just explain in brief over here. Okay, in the starting we having a nozzle part over here where N is mentioned. Here we having a medium triangle, velocity triangle, which I just mentioned in the previous lecture in the case of D level turbine. Okay, then that is a nozzle over here. That means we get a medium velocity triangle which do not have any relative velocity component, because the nozzle is the fixed part. Okay, the velocity or the jet of steam which leaves the nozzle, in that case the absolute velocity increases tremendously because it converts the pressure energy into kinetic energy. So the value of C2 is very much high. Okay, then again this enters this first moving blade. Okay, now we know that the moving blade having some motion. Okay, having some motion, that means the motion of moving blade is the velocity of blade is u. So the velocity with which the jet enters or steam enters the moving blade, that is relative velocity, that is W2. Okay, here is a maximum condition. Maximum condition is cy2 equals to 4u for this, and this is u and this is 3u. These two conditions we get for the maximum utilization condition, means for the maximum efficiency conditions. Okay, then over here this angle beta 2, this beta 2 angle is must be equals to beta 3 if we are solving for the maximum utilization condition. These two angles are same. Okay, this means W2, if these angles are same, this W2 is must be equals to W3, must be equals to W3. These two are equals. Okay, now the inlet, at the inlet of moving blade, the absolute velocity is much higher. Now we know that we convert the energy of absolute velocity to the moving blade to get its rotary motion. Therefore, at the exit of the value of C2 is must be less. So in the starting, this is outer side, at the exit it is inside. Okay, it is inside. Okay, now remember another thing. Then after the moving, we having a fixed blade. Remember one thing, either it is a nozzle or it is a fixed blade. In both cases, the velocity which enters the nozzle or the velocity which enters the fixed blade, it is always the absolute velocity. In the case of moving blade, the velocity which enters the moving blade, that is always the relative velocity. So it is the main trick in making a velocity triangle for any system. Okay, so here we having a relative velocity which enters, here we having a absolute velocity. Okay, so this is the absolute velocity which is entering over here, this fixed blade. Okay, reason is why absolute velocity, because in this case fixed blade do not having any motion. Okay, if it do not having any motion sorry, that means the velocity with which it leaves, means absolute velocity, it enters rather than the relative velocity. Okay, so it enters with this velocity, absolute velocity, so this fixed blade just guide it. Okay, now the another assumption is this angle alpha 3 is equals to alpha 2. If the angles are same, then by default the velocity of that angle is must be same. Okay, that means C3 is equals to C2 dash. Okay, so the numbering is basically 2 and 3. The number always remain 1, 2, 3. The 1 parameters always go to the nozzle inlet triangle, then 2 comes to the nozzle outlet triangle, then 3 comes to the moving blade outlet triangle. Then afterward it repeats, because afterward there is no nozzle over here, so we simply draw second, because second is for the moving blade. So in the starting, if we having only 2 stage, we mention C2 dash. If we having a 3 stage, we mention C2 dash, then C2 double dash, then if we having 4 stage, C2 triple dash. This move on. Similarly over here C3, then at this C3 dash. Okay, the number of dashes we can increase. Okay, so it is a simple way rather than numbering again and again for different alphabets to each and every diagram. So it may be little bit confusing. So with marking with the dash, it is little bit convenient. Okay, so this is the condition that is given to you, that alpha 3 is equals to alpha 2 dash, then C3 equals to C2 dash. These are equal. Okay, so it just, that means the velocity, absolute velocity of the fixed blade inlet absolute velocity is equals to the outlet absolute velocity. So this is the assumption, but practically it is not to be equal. There is a little bit drop down. Then again it comes the moving blade. So this is a single stage, then over here it is the second stage. Okay, then the relative velocity of this fixed blade, it enters the moving blade. Over here u2 equals to u2. Okay, so these are the conditions. In first case u 3u, then in the second stage u. Okay, so then it enters the moving blade. So this is a 2-stage system, and we having a maximum conditions. Remember one thing, in the case of maximum condition, the outlet velocity triangle is always the medium triangle. In that means that the outlet absolute velocity angle is always equals to 0 at in the maximum conditions that we do in the case of D-level turbine in the previous lecture. Okay, so similarly here the angle alpha 3 dash, that is equals to 0. Okay, so this line, this C3 line, it totally come in the vertical position, and this parameter cy3, this is 0. Okay, this process is totally similar to the previous article. Okay, so remember one thing, when this condition comes for the maximum condition, the outlet triangle is always the medium triangle. Okay, so that's all in this velocity triangle. Now comes to our next article. Okay, then next is the pressure compounding. The pressure compounding is the Rateaus impulse turbine. Okay, in this case we having two sets. One set is a set of nozzle which is attached to the casing, then second set is the set of moving blade. So this is the first set. Okay, then second set. The first set is the nozzle, it is fixed with the casing. Then we having a set of moving blade which are fixed with the shaft. Then again set of nozzle which is fixed with the casing. Then again set of moving blade. So it repeats as per our requirement that we needs to manufacture in our particular turbine. Okay, so this is another diagram for this. Nozzle, moving blades, nozzle, moving blade, N means nozzle, M means moving blade. Okay, so now we draw the pressure and velocity variations over here. Okay, now we know that the function of nozzle is it drops the pressure energy and converts the pressure energy into kinetic energy. But here we know that we having a different set of nozzles, first, second, third and fourth. This is first stage, then second, then third. If we use a number of stages of nozzle, then that means we do not convert the whole pressure energy into kinetic energy in single stage. That means we convert the pressure into kinetic in divided into a number of stages. In the first stage, we convert the partial pressure energy into kinetic energy. As a result, the kinetic energy increase. Okay, then this high kinetic energy steam enters the moving blade, which imparts its kinetic energy to the moving blade. It starts rotating. Then again it enters the another nozzle, which further drop the pressure energy and increase the kinetic energy. Then again that high kinetic energy enters the moving blade, which again drops down. Okay, so this process repeat as per the number of stages. So this is the outlet pressure, condenser pressure. So in this way we reduce the pressure and kinetic dividedly. So we know that if the pressure energy is very much high and it is not feasible to convert the high pressure energy in a single stage. So in this case we convert the pressure energy to kinetic energy in number of stages. So this is the first stage, then second stage, then third stage. So in this way it is practically possible to convert the pressure to kinetic in a number of stages. Okay, so this is the working. In the first case the steam enters the nozzle where it converts to the pressure to kinetic energy. Then high kinetic energy enters the moving blade where it imparts the motion to a rotor. Then again nozzle, then again moving. So this process keep on going till our number of sets that we install in our turbine. Okay, so this is all about this pressure compounding. Now we discuss about the velocity triangle for this particular turbine. This diagram is again for the two-stage system. Okay, now here above this first stage nozzle, over here above this we again get a medium triangle. Okay, that means do not having absolute velocity parameter, relative velocity parameter in that. Then this is the outlet part of the first nozzle. We know that the nozzle increase the absolute velocity, so this C2 increase tremendously. Then it again enters the moving blade. We know that the moving blade having some motion, that is u. So the velocity which enters the moving blade, that is the relative velocity u. Then it again enters the second nozzle. Now we know that the velocity which enters the nozzle, it is always the medium triangle. So we need to draw this medium triangle over here rather than slow triangle. So this is the medium triangle. Remember one thing, the inlet of the nozzle is always the medium triangle. It does not matter the nozzle and comes in the starting or nozzle comes in between. The inlet parameter is always the medium triangle. However, in the case of fixed blades, the inlet triangle is always maybe a slow triangle rather than the medium one. But the inlet is always the inlet is always the absolute velocity. Okay, so in this case the absolute velocity is a straight line, so it enters over here rather than we draw over here. So this line is the absolute line. So this is the this is the relative line, this is the absolute line. So we attach the nozzle with this absolute line. Okay, then again this nozzle increase the kinetic energy, that means convert the pressure energy into kinetic energy. So again we get the high kinetic energy. Then this moving blade having some motion, that means the relative parameter enters this, and then again we get the outlet triangle, that is the medium triangle. Okay, so this is also a diagram for the maximum condition. Okay, I hope you understand this part. Okay, now we move to our last part, that's the velocity pressure and velocity compounding. Okay, this pressure and velocity compounding system is the combination of velocity and pressure. When we attach both two systems in a single unit, we get the pressure and velocity compounding. Okay, in this case we having a set of nozzle which is attached to the casing, then we having a moving blade which is attached to the shaft. Okay, then we having a fixed blade which is attached to the casing. In this case in the single stage, this is a single stage unit over. In single stage we having one nozzle, then two rotor, between two rotor we having one fixed blade. So this is a one single stage. So this diagram is for two stage. This is first stage, this is second stage. The combination is first nozzle, then moving blade, then fixed blade, then moving blade. Okay, so the pressure and velocity variation is in the starting we having high pressure energy and very low kinetic energy. So when the steam enters the nozzle drop down the pressure energy. Okay, then it converts the pressure energy into kinetic energy as it is showing over here. Okay, pressure decrease, then kinetic energy increase. Remember one thing, in this case the pressure do not drop in a single stage because we having a two set of nozzles. Okay, if we having a three set of nozzles, then we divide the pressure into three stages. Okay, so this is first stage, we drop a partial pressure and then we increase the kinetic energy. Then this kinetic energy is also not dropped down in a stage because we having a two moving blade in a single stage. That means the partial kinetic energy drop in the first moving blade, then it guides with the help of fixed blade, then it again drop down. Okay, with the second moving blade. Okay, then after the second moving blade it enters the second stage. Okay, where the pressure again drop down and the kinetic energy again increase. Drawing this type of diagrams, remember one thing, we assume one thing, the pressure or kinetic conversion is equal in both stages. Okay, however practically it is not valid point that these lines, that means this crest part of the kinetic energy is equals to a crest part of this kinetic energy. Okay, but while drawing this diagram we assume that. Okay, so the pressure again drop down, again we get a high kinetic energy, then this high kinetic energy steam enters the first moving blade where it again drop down, then again fixed blade where it acts as a guide vanes, then again another moving blade. Okay, so this is the outlet of steam for two stage. Okay, this process may continue if we having a number of stages more. Okay, so this is the outlet velocity part. Okay, so that's all in this particular lecture. Okay, I hope you enjoyed today's lecture. Please subscribe my channel and also press on bell icon to get a notification for my coming lectures. Thank you, stay tuned.